Hi. So now we're moving on to chapter 6 from chapter 1. The reason we go to chapter 6 right now is because we basically have everything we need to understand the material in chapter 6. And we're still, it's about solving first order differential equations, but now we're solving them numerically. So we'll stick with first order differential equations for the moment. And then we will, afterwards, after chapter 6, we'll go on to chapter 2, where we will discuss second order differential equations, or higher order differential equations. Okay, so let's begin. So in this chapter, we're still just thinking about this type of differential equation where we have that the derivative of y with respect to x, or if you prefer, you can think of the derivative of y with respect to t, which is time. But in this chapter, we're just going to use x following the textbook. So imagine that we have a differential equation where the derivative is given by this formula. And we remember seeing when we were looking at slope curves that what this differential equation is telling us is that the solution, y equals y of x, if you were to plot this, the graph of this solution that is going through the point xy, then this formula here tells us that the slope of that graph, or the slope of the tangent line to that graph, is precisely given by f of xy. So we can very easily determine what the slope of a solution is going through any point that we like. We just plug in x and y into this formula, and that gives us the slope. So we'll see how we can use precisely this formula, and it can be actually a very complicated formula, something that's really, hard to approximate, very, it's just hard to integrate. So this could be something that makes us very, very unhappy, something that's just impossible to solve by hand or symbolically. But the techniques in this chapter, they don't care. It's as long as we can, evaluate this function, then we're fine. Okay, so how does this work? And by the way, this is principally the way that differential equations are solved. It's by solving them numerically. I guess we even saw in GeoGebra, we were using solve ODE, but we were also using nsolve ODE, which is this numerical solve. So we're going to learn what that nsolve ODE function is doing. Okay, so we have our differential equation and we have an initial condition. So how can we use this idea here in order to get an approximation for the solution very easily? So the idea is the following. So right here, I've drawn the actual solution of this differential equation. Typically, this is going to be something that's unknown. So we won't necessarily always have access to be able to know exactly what this is, but just imagine we know what this is for the moment. So this is our true solution. And what we're going to do is approximate this solution at different points. We're going to start with the initial x, that's our initial x right there, and our initial y. So we know that the solution is going to start by going through this, this point here, x naught, y naught. And what can we do when we're at this point? So we don't really know anything about this function, but we do know something. We know that it goes through this point and that it has a slope of, well, we just plug this point into the formula, f of xy. So we plug this in and we get a slope, and say that slope is going to be this m naught, right? So we know the we know that the solution goes through this curve, through this point, and this curve has a slope of m naught. So let's just assume that the slope over this entire interval from x naught to x1 is precisely this m naught. So if we assume that the slope is m naught through this whole interval, then we're going to follow this straight line. We're just following this tangent line here. And that will eventually take us to this new point. So how far do we go? Well, we just go from x naught to x1, and will get us to this new point here. And then we will just repeat that process again. So at this point, we plug in x1, y1 into the formula. That gives us our slope m1. We follow a straight line using that slope. We go from x1 to x2, which is a distance of h, and that gives us our new point. And again, we plug this into our function, gives us a new slope, and we just travel along that line from x2 to x3, and that will give us this point here. So that's the basic idea, how we can continue to use this f of xy formula that is giving us the slope of our solution. We just keep doing it in this way. And the idea is that perhaps if we make this h smaller and smaller and smaller, then this approximation will get closer and closer and closer to our true solution. And hopefully at some point, they'll just look exactly the same, that the error is so small that if we're to plot both on the same plot, you couldn't see the difference visually. Okay, so h is going to be our step size. You see how we're always taking a step of h between each of these x values. So to go from x naught to x1, we just add h to that, and that gives us x1. And then we add h to x1, it gives us x2. Add h to x2, and we get x3. So what is x1? Well, x1, we just get it by taking x naught and adding h to that, and that gives us x1. Okay, what about y1? Well, y1, we're going to use the fact that we're going to let mi be the slope of the solution at this point. So the slope is given by just taking this function, this formula, f of xy, we plug in x naught, y naught, and that will give us our slope. Oops, this is supposed to be a 0. So that is our slope. Aha, oh, I need to change it in a few places here. Okay. I had a change of notation at some point. There we go. Okay. So there's our formula. I just think it's a little bit nicer that m naught is equal to f of x naught, y naught. That makes a little more sense. So let's use that notation. So what is the equation of this line here? What is that equation? Well, we know that a really nice formula for the equation of a line is the so-called point slope formula, which is right here. So this is our point slope formula. And it simply goes y minus y naught equals slope m naught times x minus x naught, where this line goes through the point x naught, y naught, and it travels using the slope of m. So that's our point slope formula for a line. So what is y1? So that's the question we're trying to find out. What is y1? Well, we just plug y1 into here and x1 into here. And then we know what x1 is. We have it from up here. So we'll just plug that in. And what do we get? Well, notice we get x1 minus x naught right here. And that is precisely h, right? So we can see that from up here. x1 minus x naught, that's equal to h. So this thing's going to be h, so we'll put h there. And we can move this y naught to this side of the equation, and that ends up giving us this equation right here. So y1 is equal to y naught plus h times the slope m naught. And if we now substitute in the formula for m naught, then we get this very nice equation here. So it's very simple. So to get the y1, we take the old y naught and we add our step size times whatever the slope is at our current point, x naught, y naught. And that gives us our new y1 value. Okay, so notice there's no integration involved here at all. This is simply just arithmetic. So that's the beauty of these numerical methods. No antiderivatives, no derivatives or anything, just numerical arithmetic, and it's going to give us very good solutions to our differential equations. Okay, so what are the other formulas? Because you saw up here, we're actually, going to x1, y1, then x2, y2, and x3, y3. So what are the formulas for these guys? Well, they're precisely the same. x2 is x1 plus h, and y2 is equal to y1 plus h times the slope at x1, y1. And x3, we take a step of h, and when we take a step of h in the x direction, that gives us, if we follow this tangent line, we'll go from y2, and we will move h times the slope at the point x2, y2, and that gives us our new y3 value. So there's lots of different ways to say this equation, but it's a very simple equation, and it's going to be very easy for us to use to approximate our solutions. So the general formulas then for Euler's method, so this method is called Euler's method in this section 6.1. The general formula is that to get the next x value, you take the current x value and you add h to it, and that gives us our next x value. The next y value, we take our current y value and we add h, our step length, times the slope of the curve at the point x, at our current point, xn, yn. And that's it. So you see, all we need to do to apply this method, we just need to know this function. That is the key. So as long as we know what this function is, then we're golden. We just need to decide what is our step size, h, and we'll try a bunch of different step sizes and see what happens when we take different step sizes. And the other thing we need is, of course, we need our initial condition as well. So we do need to know what is our initial condition, y of x naught equals y naught. So we need to know our initial point that we're going through, x naught, y naught. So those are the ingredients that we need to use Euler's method. Okay, so let's see how this works in practice. So let's have a look at this formula, at this differential equation here. So here's our differential equation, y prime equals x minus y. So this is our formula, f of x, y. Here's our initial condition, x naught is 0, y naught is 1. And here is the true solution. So we actually know how to solve these types of equations now, but we won't go through that. This is the true solution. It's pretty easy to check or to solve it by hand. And we're just going to use this to compare. Normally you wouldn't have the actual true solution like this in practice, but this will allow us to see how much error there is in this approximation. So we're going to start with a very pretty small step size of 0.1, and we're going to approximate the solution y of x, the true solution, this one, we're going to approximate it at these different points. 0.1, 0.2, 0.3, 0.4, 0.5. So that corresponds to the step size of 0.1 because each time we're going up by 0.1 to go from one to the next. And we're going to use Euler's method. Okay, so let's get started on this. So first of all, let's note some things. So note f of x, y, this is equal to x minus y for this problem. And we also notice that our initial point, x naught, y naught, is equal to 0 for x naught and 1 for y naught. And that just comes from this initial condition. X naught, y naught, right there. Okay, so now we're good. So now let's get started and use our formulas to compute x1. So remember that's x naught plus h. So that's 0 plus 0.1. It gives you 0.1. And y1 will be y naught plus h times f of x naught y naught. Okay, so y naught was 1. H is 0.1. And then f of x naught y naught, this is equal to, well, maybe we should, it might be helpful to calculate this separately. So let's just do this separately. So we'll call that m naught equals f of x naught y naught. So that is going to be x naught minus y naught in this case, because that's our formula here, x naught, x minus y. So that will give us 0 minus 1, so we get minus 1. Okay, so that's what f of x naught y naught is. So let's plug that into our formula here. So we get minus 1. And when we calculate this out, we will get, let me just write it on the next line. So y1 is equal to 0.9. Okay, so there's our next point. Okay, so now let's do x2, x1 plus h. This is 0.1 plus 0.1. That gives us 0.2. The slope at this point is going to be x1 minus y1. So that gives us negative 0.8. And y2 is equal to y1 plus h times, maybe I'll just call this m1 to make things a little bit easier. I'll do the same up here as well, just so we don't have to write so much. This is a little bit tedious to do by hand, so it's probably nice. Oh, let me just erase this. Yeah, let's make this more compact here. So it's a little bit tedious to do by hand. We'll see in a bit how we can do it on the computer. I'm probably going to start using the computer pretty soon here to do these calculations. So let's see, y1 is 0.9 plus h times negative 0.8. Okay, I'm already deciding to use my my computer to do this calculation. So 0.9 plus 0.1 times minus 0.8. Okay, so that is 0.82. So maybe I'll just highlight these numbers that we're getting. So we have x1 is this. Okay, so I'll highlight this stuff too. That's x naught, y naught. We have x1, y1, and we have x2, y2. Let's keep going. x3 is x2 plus h. 0.2 plus 0.1 equals 0.3. The slope at this x2 point, x2, y2, is equal to 0.2 minus 0.82. 0.2 minus 0.82, negative 6.2. Sorry, negative 0.62. And y2, y3 is equal to y2 plus h times m2. So that is 0.82 plus 0.1 times this slope. And that is going to be 0.82 plus 0.1 times, you're going to be amazed how fast this is later. I'll show you how to do this on the computer very efficiently. So this is going to be, let me just move this over a bit to make room. This is 0.758. x4 is, I hope you don't mind me skipping this step. You just add 0.1 again. So it's obviously 0.4. And then m3 is f of x3, y3. This is going to be 0.3, right? So that's our previous point right there. So 0.3 minus 0.758. 0.3 minus 0.758, negative 0.458. That's our new slope. You can see things are getting a little bit more complicated here. We have 0.758. Maybe, so let me write down the formula first. y3 plus h times this slope, and that is equal to 0.758 plus 0.1 times negative 0.458, and that is equal to 758 plus 0.1 times negative 0.458. Okay, so that is going to be 0.7122. Yeah, so that's it. So there we go. And we just have one more to do, almost done. So finally we have x5 is 0.5. Let me just do this here. M4 is f of x4, y4, and I'll just calculate that directly. So this is going to be 0.4 minus 0.7122. Maybe I'll write that in. I'll write that in instead. 0.4 minus 0.7122. Negative 0.3122. And y5 is going to be, I'm going to take a shortcut here again. So it's the old y value plus 0.1 times the slope and let's calculate that. 0.7122 plus 0.1 times negative 0.3122. Okay. 0.68098. And that is it. There's our last points. So let's summarize this maybe in a table. So we'll have n, and then in this, and so n will be 0, 1, 2, 3, 4, 5. We have xn, 0, 0.1, 0.2, 0.3, 0.4, 0.5. We have yn. So this is a little bit trickier. Oh, maybe I can grab it from my screen. So yeah, it's 1 and then 0.9. Yeah, okay. So 1, 0.9, 0.82, and then we have 0.758, and then we have 0.7122 and 0.68098. Okay, the moment of truth. Let's calculate the true value. Remember, y of x is the true value of the solution. So I'm just going to enter this in my computer here. So what was the true solution? We have it up here somewhere. So the true solution is 2 times the exponential of minus x plus x minus 1. Okay, and I'm just going to plug in all these values of x into this formula. And I guess I'll round it to, I don't know, maybe I'll round it to like 5 decimals. Okay, so here's what I get. So of course it is 1 for the first value, and then the second value is 0.90967 approximately. So that's actually a pretty good match. Just make that a little bit smaller. So that's actually pretty close to the value we predicted of 0.9. So our estimate is not too bad. The next value is going to be 0.83746. That's our next value. Again, it's pretty close to our estimate of 0.82. And then the next is going to be 0.78164. Okay, looks like the error is getting a little bit larger than it was in the previous points. Next we have 0.740, oops, 064. Like that. And then finally we have 0.71306. So these are all rounded to 5 digits. So yeah, it looks like each time we're getting, something that's pretty close, so we can see there's some errors that are occurring here. It might be nice to actually write down what these errors are. Let me just quickly calculate those and write those down. Okay, so here are the errors. So these are going to be the true values. So that's the true actual values of the solution minus these approximations. So initially the error is exactly 0, which is not a surprise. That's what always happens with the initial point. And then the next value is going to be 0.00967. And then we'll have 0.01746, 0.02364, and then 0.02844 and 0.03208. So as we suspected, just looking at these numbers here and comparing them to these values, it looked like the error was getting larger as we were going down this way. And we can see that precisely now by looking at these actual error values, that with each value, the error is going up. And that makes sense because each value is depends on the value before it, but the value before it was an approximation. And so you see how the error is actually accumulating here in this process, right? And this is what we saw sort of back here in this picture. We can see that these error values, so initially there's no error, and then here there's a small error, but then the error gets larger and larger, right? And that's because this error is a combination of this approximation error, where we're approximating this curve with a straight line. So there's an error there, but it's also, this error is because there's an error here as well. So this error is just sort of accumulating and getting larger and larger. And this is something that we will also see when we look at, even when we take smaller values of h. Okay, so there's our table of numbers and our approximation. So now let's head over to the computer, and we will do we'll do an example in Julia. So this will be a Julia code demo. Okay, so we'll head over to the computer and we will look at doing a Julia code demo. Okay, so here we are in Julia. I think I'm sharing. I think I'm sharing my desktop. Yeah. Okay. So this is the website for the Julia language. It's julialang.org. If you just Google Julia Lang or Julia language, you will find this website. So Julia is a free and open source programming language, and it's designed specifically for use with like data science or scientific computing, these sort of technical computing topics like in engineering or in any of the sciences. And it's now becoming really big with like data science and machine learning as well. So this is Julia. I've been using it for a number of years, and it has a very nice syntax. It's a very high-level language. It's easy to program in like Python, but it's also naturally it's very fast, which means that you can write code at a very high level, but the code will perform very well. So to download Julia, you can click here on this download button. Oh, and I see there's a new version of Julia that I don't have yet. Oh, so well, why don't I just download it? So pick your operating system. So I have a Mac OS, so I'm going to choose this, but it's available for Windows, Mac OS, Linux, and so on. So I'm going to download this. And I will open it up. So I'll show you how to do this on a Mac. On Windows, I think you'll download like an installer. Yeah, it says it's an installer. So you just run the installer and it will install Julia on your computer for you. So on a Mac, you end up getting this window. And so to install this on a Mac, you just drag it over to your applications folder. And I got this message here, which is asking me, do I want to replace the one that I have? And I will say, yes, I want to replace it. Okay. So now I'm done with this. Don't need this anymore. And I already have my launcher right here. So I'll just click on the launcher and this should open up Julia 1.5.2. Are you sure you want to open it? Yes, I am. And here it is. Hopefully soon. Okay, there it is. Version 1.5.2. Perfect. Okay, so let me just zoom in on this a little bit better so you can see. Okay, so this is the Julia program. And this is at the Julia prompt, we can enter our commands. So I'll show you this in a second, but first I wanted to just mention that if you type question mark, you will get a help prompt. So that'll change that prompt into a help prompt, and you can ask, you can type the thing that you want to search for here in this help. To get out of it, just hit backspace. And there's another thing here as well. It's this square bracket. So if you type square bracket, it gives you a package manager. And again, if you press the question mark and hit enter, it'll tell you about the package manager. One thing I want to do is make sure I add the plots package. So you should do this as well. And that way you'll be able to do the plots that we're going to do today. So add plots. This may take a while, so I won't make you watch this. Okay, so it's done. That didn't take too long. Now I'm going to hit backspace to go back to the Julia prompt, and I'm going to type using plots to load up this package. And the first time you do this, it's going to take a while to do this pre-compiling. So I will pause and we'll be right back. Okay, so that's done. All right, so we'll use that later, but I just wanted to show you initially like how to add packages. So you can do status to look at the packages that you've added. I think I have a lot of packages added, but the one that we're most interested in here is this plots package here. So we've got that all ready and we've loaded it up by saying using plots. So the next time you type using plots, it won't take as long because it doesn't have to do that pre-compilation again. So although this is taking some time. Aha, something strange. I think I'm going to exit Julia and come back in again. So let me just, I hit Control D there, and that will exit Julia. So hopefully this exits cleanly. Okay, there we go. Yeah, so let me just close that and open Julia up again. All right. There we are. Okay. Oh, looks like I think it's because I updated plots. Okay, so this will just take a bit of time. 1 sec. Okay. Yeah, so pre-compiling plots always takes a bit of time, but once it's pre-compiled, it should be much faster the next time. Okay, so now we're good to go. All right, so we want to solve this differential equation. Y prime is equal to x minus y, and the initial condition is y of 0 equals 1. Okay, so that's what we're going for. Let me just close this Julia window there. Yeah, so the hash mark here is just to create a comment. So that's not going to execute anything. But it's just to remind us the differential equation we want to solve. So our function is f of xy equals x minus y. So this creates a function in Julia, and I can now evaluate this function, say at 0, 1, which is our initial point, and that will give me -1. Okay, so that's how this function is going to work for us. And what we want to do now is start with like an initial value for x. Say our initial value of x is 0, and our initial value for y is 1. And our step length is going to be 0.1. So each new value of x we're going to get by adding h to it. So our new value of x is going to be x plus h. Maybe let's do this. I think this is a little bit more confusing. So let's just go ahead and actually do it. What I really want to do is create like an array of points. So let's do it this way. So we're going to go over the interval from a to b, which is going to go from 0 to 0.5. So that's the first x value is 0 and the last x value is 5. And we're going to make 5 steps. So n is going to be equal to 5. And so we can compute the h as b minus a divided by n. And that gives us our 0.1. So that'll be useful to know. And then actually I want x to be an array. Initially I'll make it all zeros, and it's going to need our initial point and then 5 more points. So that'll be zeros n plus 1. And our initial point will be this a value, which is 0, so that doesn't change anything. And then y will be zeros of n plus 1 as well. But our initial y value, we want it to be equal to 1. 1. So now our y array looks like this. Okay, so we're going to fill in these values now. So x2, this is going to be x1 plus h. And y2 is going to be y1 plus h times this function is going to give us our slope at the previous point, x1, y1, like that. 0.9, so that's what we had before. And now we just need to repeat this again. So now we'll do x3, and we'll do the same for y. So this has to become a 2 and a 3.82. That's correct. And then we'll do the x value next. I'm just hitting up arrow to get my previous commands here. So 3, so x4 is this, yes. And then notice there's a bit of like floating point error due to round off, or yeah, it's due to round off. So it's because we can't put this number precisely on the computer, represent 0.38 precisely. So the closest number on the computer in floating point arithmetic that we can represent is this number, which has this 4 out here. So that's what's going on there. So don't worry about that. When I read that, I know that that is 0.3. Okay, so x4, yeah, so we did this. So let's do the y value. So y4 is y3 plus h times x3, y3, 0.758, yep. And then x5 is equal to y is x4 plus h, and y5 will be, so you notice this is quite repetitive. There is actually an easier way to do this, which I'll show you in a second. But we're almost done. So let's just do the last value, x6. Notice that Julia starts counting its arrays with 1 instead of 0. So that's why these indices are one off from what we were doing in the notebook. 5, almost made a mistake. 5. There it is. So those are all our numbers, and we can compare them with the true function. So the true function is equal to 2 times the exponential of minus x, and now I forget what it was, plus x minus 1. So that's our true function. So what we have is x and y. It looks like this. So those are our x values and our y values. Maybe I'll put this in a data frame. So using data frames. So I use data frames in order to make this into a nice table of values. Of course, I have to pre-compile this because it's the first time I'm running this. Okay, and as soon as I pause the recording, it finishes. Okay, so let me just make it a data frame to make this look a little bit nicer. So x values, y values, like that. So this will look nice. Okay, so there are the x values and the y values, so that looks nice. And I also want to add in the true values. So y true is equal to y true, and I'm going to run this function on each entry of x. So we use this dot notation for broadcasting this function across this entire vector. So that's a quick way to calculate all those values there. Yeah, and that matches what we have in the notebook as well. Okay, so I mentioned there's a faster way to do these, the calculation that I just did. Instead of doing each thing individually and changing those indices, I can just say for n in 1 through n, I can say x n plus 1 is equal to x n plus h, and y n plus 1 is equal to y n plus h times f of x n y n. Right, so that'll be a lot easier. So this for loop is going to start with n equals to 1. And so that'll calculate x2 and x and y2. And then the next iteration, n will be 2, and it will count, it'll calculate x3 and y3, and so on. So this 1 colon n means the integers from 1 up to n. So this will be, n is 5 here, so it'll be 1, 2, 3, 4, 5. That's what this 1 colon n is. And that's it. And hit end. And that just does it all at once for me, very easily. Okay, and we can see that we get the same x and y values here after I ran that code. Okay, great. So, and to make our lives to make our lives even better, we can actually write a function which will do this whole Euler method for us all at once. So how would we do that in Julia? Well, when we wrote these simple functions like f of x, y, like this, or y true, so these are functions in Julia, but in order to write a more complicated function that has more than one line of code, we're going to use this word function. And this Euler function is going to take the function f. So we'll tell it what this f function is. And then it'll take our initial y value. It's going to do the Euler method over the interval from a to b. And it's going to take n steps. Okay. So this is our Euler function. So the first thing that we'll do is we'll compute our step length. So this is going to be b minus a divided by n. That gives us our step length. Then as we did before, we're going to create an array for the x values. So it needs n plus 1 values. And same for the y. The original initial x is going to be a, and the initial y value is going to be y naught. And then we'll do our slick little for loop for n in 1 to capital N, x n plus 1 is equal to x n plus h, and y n plus 1 is equal to y n plus h times the slope. Okay, and the for loop, and we will return the x array and the y array, and then we'll end the function. So that's how you create a function in Julia. It's very nice, easy syntax, especially if you're used to MATLAB or Python. This is very similar to MATLAB and Python. Okay, so let's see how our function does. So we have our, we'll run this function like this, x comma y equals Euler of f, and then y naught a comma b comma n. So I think I'm going to get an error message here. Yeah, y naught is not defined. So y naught is 1. That's what we had. Yes, y naught is 1. Okay, let's run this again. So I just press the up arrow a couple times. And let's run this. And there it is. So it's actually printing out here the x array here and then the y array. And if you don't want it to print that out, you can put a semicolon here and that will stop it from printing it out. But it'll still have those values in the x and y array. So what's great about this is now we can very easily try an increased number of points, right? So we were doing 5 initially. So we can do now 10 points. And there we go. We just ran Euler method with 10 steps instead of 5 steps. So it makes it very easy for us to now try it on a bunch of different values. And there's Euler using 20 steps. So in order for us to see, how accurate, what is the accuracy now for running Euler method with more steps? And this is where the plots package is going to come in. So let's start by plotting our, well, actually, so maybe before we do this, because writing plot functions can get kind of tedious. So I think a really nice way to do this is to, let's put the code into a file, and then we'll just load the file up. So let's see here. I'm just going to create, I'm going to use my favorite editor, which is Vim. I have a Mac Vim on my computer. So I'm going to create a new file. Let's call it Euler.jl. Okay. So here's this Euler function right there. Okay, perfect. All right, so I'm going to actually grab this code here, and I'll just throw it in here. Okay. All right, that looks good. Make that a little bit bigger. All right. And then let's see, what else do we need? We need the plots package and possibly the data frames package as well. All right, perfect. And what was our first example? So our first example is f of x comma y is equal to x minus y. Y naught was equal to 1. A comma b is equal to 0 comma 0.5. And n, well, n we're going to change. So we'll just change that. So now we can do like x comma y is equal to Euler of f y naught a comma b comma 5. And let's say that that's the, well, let's leave it at that for now. And what else do we need? We need the true function. So y true is 2 times the exponential of minus x plus x minus 1, I think. I always have to check this. Yeah, okay. All right, so there's all the code there. I'll just save this file. And now you'll see that all I need to do in Julia is to So first of all, let's just make sure that that function is there. If I hit semicolon, I get a shell, and I can just do ls Euler.jl just to see that it's here, and it is here. So it's in my current directory. So I just need to do include one second. Okay, so I just include Euler.jl. Oops, .jl. There. So it's going to run all this code in this file for me. And there you see. So it's outputting the last thing that I ran, which is this Euler. So it's outputting that. Okay, great. So so what do we want to do? So we want to plot this true function from A to B. So let's start with that and see what we get. So let's run this code again. So this plot command is taking a bit of time, but it'll show up pretty soon. Okay, it popped up on my other screen here. So there it is. So that's what this true function looks like. Let's see, maybe I'll just put this up here. That'll look nice here. All right. Let's see, I'll just make this smaller. Okay, I can maybe, I like to see this plot nice and big. So let's do this. Make this bigger, like that. There we go, nice and big, perfect. Okay, so there is our plot. And what I'd like to do is I want to modify this plot. So I'm going to do plot bang, which will modify the previous plot instead of giving me a new plot. And what do I want to plot? I want to plot the data points x comma y. And let's see, there's some special things I want to do. Oh yeah, so one thing, let me add a label to this. So we need to put labels on things so we remember what is what. So this is going to be the true solution. And we're also going to give a label here. This will be n equals 5, just to remind us that this is what happens when we took 5 steps. And I want the marker to be a circle, and I want it to be a small circle, so marker size 3. And I also want, well, maybe I'll just leave it at that. That's probably good enough. So I just wanted to have like a little small circle. Okay, so let's run that and see what we get in the plot. So there it is. So perfect, perfect. Okay, so that was a lot of work, but now we have this really nice plot on our screen here. And now we can add more to see what happens. Let's see what happens when we now do 10 of these. So I'm going to just copy paste this. And I think the first one I'll call x1, y1, and then the second one will be x2, y2. And I'm going to do 10 points here. So this is going to be x1, y1, and I'm going to copy paste that and change this to a 2 and a 2. And of course, this is now with 10 steps instead of with 5 steps. Okay, so let's see what happens now. Boom, there it is. So now the code is running much faster. So in Julia, once things are compiled, then it runs really fast. But sometimes the compilation takes some time. And what we noticed is by doing twice as many steps, or in other words, we're dividing our step length in half, it looks like the error has also been divided in half, roughly. And indeed, this is the case. So it's not exactly a half, but it's approximately a half. And there's actually a mathematical theorem that says that we're guaranteed to have approximately a half. The error is divided in a half when we divide the step length in a half. So there's a more precise statement there. But let's do this again with 3, and we'll again double the number of steps. And let's see, 3, 3, and 20. Okay, so let's run this. Oh, did I make a mistake somewhere? I did. So it just told me that these two arrays were not the same size, and that's what it was complaining about. And indeed, x3 has twice as many points as y2 did. So that's why those weren't the same size. But x3 and y3 are the same size. Okay, so that's what this error is. If you scroll up a bit, you'll see it says bounds error, attempted to access 11-element array at index 21. So yeah, so that's what happened there. Okay, so that's no big deal. Fix it, we run it again, and there we go. So you see again, it looks like the error between the approximation and the solution is approximately divided by 2, once again. All right, and there's actually a really interesting technique. So once we sort of know that the error is divided by 2, it kind of makes sense to like take this original solution and subtract from it twice this amount, and that would give us something that's very close to this. And that's a technique called Richardson Extrapolation, which you may learn about if you ever take a numerical analysis class. And you might think that maybe it would give us exactly the solution, and it doesn't, but it does give us a really good approximation. So you can kind of combine 2 of these approximations together in a smart way and get an even better approximation. So that's called Richardson Extrapolation. All right, so this looks pretty good. I think if I was to plot any more, it would just it would get kind of messy here, and but you can see that it's gradually getting to be a better and better approximation of the true solution. So this is how Euler's method works on this problem. But let's have a look at another problem to see what are some of the issues that may occur with Euler's method. So it seems like it's a pretty good approximation, but sometimes it can be hard to get a good solution. So the next problem I would like to look at is this one from the textbook. This is, in the textbook, it's example number 4. So it is y dy dx is equal to y times cosine of x, and the initial value is equal to 1 again, and the interval that we're going to look at here is from 0 to 4 pi. And in Julia, you can enter \pi and then hit tab, and it'll actually give you the pi symbol. And when you have a number and then something like a variable after it, you don't actually need to put the times in Julia. So you can actually just put 4 pi, and that'll actually do 4 times pi. Okay, so we're going to do this, and then I'm going to take, let's see, what else do I need? I basically need all of this, but I'm going to modify it. Let's see. So the true solution for this problem is going to be, let's see, just want to delete all this. So the true solution is the exponential of sine of x. Okay. And we're going to start with, according to this suggestion, we're going to start with 50 points, and then we will double it each time. So we'll do 100 points, and then we'll do 200 points. And that should do it. Oh, I just want to modify these labels here as well. Okay, so definitely not something that you would ever want to do by hand. You can see the power of using a computer to do something like this for us. Now, maybe I'll just comment this stuff out here, because I don't really want to run all this as well. So I'll just comment that out. So you can comment stuff, you can comment out a block of stuff in Julia by putting hash equal and then equal hash to comment it out. All right, so let's run this code. And there is our solution. Ooh, so it's getting kind of messy with all those dots. Maybe I'll remove those dots from here. Let's see. Is this what I wanted? Yeah, I think so. Yeah, it's just too many dots. So maybe I'll just remove it. Definitely I'll remove it on the on this one here. Let's see what that looks like. Okay, so I wanted you to remember that these dots are telling us that it's like discrete values. So don't forget that we're just computing a bunch of discrete values. But when you join them up with straight lines, when you plot them, it makes it look like a nice smooth curve. So yeah, let me just delete all of this stuff as well, so we can see it a little bit better. So there you go, and you can see how it's like, you know, just a bunch of straight lines joined together when you look at like this orange solution here. But then as you're adding more and more points to your approximation, it becomes less and less, you know, like a bunch of straight lines joined together, what's called piecewise linear. So it appears less piecewise linear, and it appears more smooth, like this purple line. But this is still a piecewise linear function. But you can sort of see how as we're adding more and more points, we're approximating the blue solution better and better. Sometimes we'll like overshoot it like this, but for the most part, it looks like we're kind of like undershooting it. And it looks like it's going to take us quite a few points in order to get a good approximation. And that's the problem with Euler's method, is that it does actually require a very large number of points in order to get good approximations. Sometimes it can be just far too many points, where it could take, you know, days or weeks or even, you know, millennia to, you know, use Euler's method with enough points to get the accuracy you need. So we're going to look at more accurate methods in the future. Typically, Euler's method is not really used much in practice because there's much better approximations. So you see, even though I'm like doing 400 points now, it's still, there's a significant error, you know, around x equals 8. So it is not doing an extremely good job of approximating this function. With the other problem that we were looking at, this would have been more than enough points to solve our first example. But on the second example, it's just the true solution is rapidly changing so much that the Euler's method is having a lot of trouble keeping up with this drastic up and down motion. So, well, I think that's probably a good place to stop. I encourage you to download Julia and try to follow along and go through the same process that I went through here, where I encourage you to type up this code and run these examples on your own computer with Julia. So I hope you enjoyed that. Next time we'll look at a method called the improved Euler method, which is going to give us a much better approximation. Well, actually, so maybe there is one thing that we could do here. No, I think that's fine. So I just wanted to maybe give you more evidence that, in fact, the error is getting divided by 2 each time. But I think you'll believe me. So if you want to see this more precisely, there's some nice tables in the textbook that show you how the error is approximately divided by 2 when we divide the step length by 2. So, okay, so I'll stop there. Thanks so much. I'll see you guys in the next one.